Hey guys, welcome back to Cougar Chem Tutoring. I'm Austin and I'll be running through part 3 of problem set 8, orbitals and electron configurations. Alright, number 11, how many valence electrons are in sulfur? What ions is sulfur most likely to form? So the easiest way to do this is to figure out what the electron configuration looks like and to count the valence electrons from the same number, principal quantum number. Okay, so here I'm going to say, okay, I know I have 1s2, so let's find sulfur. Here's sulfur right there. Okay, so to get there, I had to go through the 1s2, 2s2, 3s2, and then I skipped up 2p6 over here, 2p6, 3s2, and then up to 3p, 1, 2, 3, that's 4, 3p4. Okay, so that means if I were to write, let's write the condensed version down. So I got neon, 3s2, 3p4. Okay, so valence electrons will always come from the principal quantum number. So if they have the same principal quantum number and you have that many electrons in there, you'll add all of those together. So we're going to add the 2 from the 3s because we're in the same shell as the 3p, and then all the electrons from the 3p. So that's a total of 6 valence electrons. Now, if you remember from the last video, what we're trying to do is to get to the ideal octet, okay? And the way that we do, the way that you may hear that as well, called as well, is a noble gas configuration, because noble gases automatically have 8 valence electrons, which is why they're relatively unreactive. They don't like to give away or accept any electrons. They're happy where they're at, okay? So how many valence electrons are in sulfur? We got 6. And so what ions is sulfur most likely to form? So an ion is a charged particle that we get by either gaining or losing an electron, okay? So if we want to get to 8 from 6 valence electrons, what would we have to do? We would have to add either add 2 or lose 6, and the easiest will always be the one with the least amount of work to do, so the least amount of electrons to move around. So that's going to be 2, so that we would be add 2 electrons, and that would mean we'd get a minus 2 ion, which is a type of anion, a negatively charged ion. Okay, so that's how you kind of want to think about ions and how to find what kind of ions each element will form. Okay, so letter B here, how many valence electrons are in barium? Okay, and what ion is barium likely to form? Okay, so let's find barium. Barium is right there on the periodic table, if you can kind of see right there. So to get there, I'd have to go through a bunch of these things. In fact, I'm going to just skip to the condensed electron configuration just because it's going to be easier. So I've got xenon, and then I got, let's see, 6s, right? 6s, and then this would be 2, 6s2. So how many valence electrons does it have? It's got 2 valence, okay, electrons. Now, is it easier for this thing to gain 6, right? We're at 2, we want to get to 8. To gain 6 electrons, or to lose 2? And the answer is lose 2, right? Lose 2. So we would be short 2 negative charges, which would give us a positive 2 ion, which is a type of cation. Okay, so that's how we look at how each element is going to create an ion or not, is based on the electron configuration, how many valence electrons it has, and the potential to getting to the octet. And if it does, then how many will it lose or gain? Okay, all right, so number 12, determine whether the following atoms are paramagnetic or diamagnetic. What that means is in any given shell, let's say I have the 2p subshell, and remember that in the 2p subshell I've got the 2px, the 2py, and the 2pz. Okay, paramagnetic is only means that electrons are unpaired. So para is kind of counterintuitive because you might think paired to start with, but it's actually unpaired. Okay, so unpaired electrons, meaning you'd have let's say here's 3 upspin electrons in each one of the orbitals, following Hund's rule, right? We can only fill in 1 orbital at a time, and then go back to fill in double to pair them up. Okay, so this would be considered paramagnetic. In fact, it would consider to be paramagnetic until we actually filled in this last one right there, right? This last one. Without that last one, that last electron right there, this was still paramagnetic. Once all the electrons are paired with another electron, it's considered diamagnetic. Dia meaning 2, okay? Dia meaning 2. So, without this one there, that was considered paramagnetic, okay? And the second I added it, it became diamagnetic. So every other configuration here would have been paramagnetic because we couldn't have them all paired without filling it up, okay? So let's see if we can kind of expand on that as we go through this. So Na+, what that means is, okay, Na+ is right, Na is right there. Okay, so it originally had a 3s1, right? 3s1, but it lost this guy. So what was left? After we lost 3s1, we had a 1s2, 2s2, and 2p6, right? And if I were to draw out all those orbitals, so 1s2, it's got 2 electrons in it, right? And then the 2s2, sorry, 2s2. I draw a 2s orbital. So 2s orbital, 1, 2. And then I got 2p orbital up here. So here's a 2p, 2s, and 1s. Okay, so I got 1, 2, 3. And then this was filled, 1, 2, 3, 4, right? And this is what we ended at because we lost the 3s1 over here. We got rid of it. So yeah, this is going to be diamagnetic. I'm just going to put a D for diamagnetic, okay? All right, so let's see if we can continue to understand this. So calcium is right there on the periodic table. Okay, let me go ahead and erase some of these circles so you can tell where I'm circling here. So I am circling right here. That's calcium, okay? And that happens to be in the 4s orbital. Okay, so up to the 4s orbital, we know that everything else was paired, okay? But calcium it ends with 4s2, right? Which means, and we know there's only one s orbital, and if it has both electrons, then that must be diamagnetic, okay? Because there are no unpaired electrons. So diamagnetic. Okay, regular fluorine. Where's fluorine? Fluorine is right there, okay? We went through the 1s2, and then we went to 2s2, and then we got to 2p, and we got 1, 2, 3, 4, 5. Okay, so we got, so if I were to draw this out, right, let's use this diagram I have here. Okay, I've got the 2p, let's go ahead and redraw this, sorry. 1, 2, 3, 4, 5, and then 5, like that. So I've got this guy unpaired, right? Unpaired. If this was F minus, this would be considered paired, right? They would all be paired. But because they're not paired, this is going to be paramagnetic, okay? So that means there's at least one unpaired electron in the atom, in the electron configuration. Okay. All right, D, we got lithium, kind of getting the pattern here. Lithium, we're in which orbital? We're in the 2s orbital, and we're going to 2s1. You can already tell we're in the if we're at 2s1, that one electron is going to be by itself, so this is going to be paramagnetic. The reason that we like to distinguish these, by the way, is because substances that are paramagnetic actually exhibit magnetic properties. So these, I'm just going to put magnetic under here. Magnetic properties, including gases and things like that. They'll actually react to magnets and magnetic fields. And that actually helps us a lot with applications in science and there are some tests that we use to use these properties for, okay? So that's why we're distinguishing these. All right, so magnesium, where's magnesium? It's right there, okay, on the periodic table, which means we're in the 3s, and we did have them both filled. So it was 3s2, but now we lost both of them, and we're back down to the configuration of neon, which means it was diamagnetic. All of them are paired up to that point, okay, up to that point. All right, Br minus. Okay, Br is right there, and that would have. Let's see. Let's just look at the valence shell really quick because we're obviously going to fill in the whole D block here. So we got 4s2 and then 4p. Originally it was going to be 4s2, 4p. Let's see, 5. Right? It was originally 5, but then we added an electron by giving it a negative charge, which made it 4p6. Right? 4p6. Which, if you were to draw out the s orbital and then the 3p orbitals, okay, we'd get 1, 2, 3, 4, 5, 6. Yeah, these are all paired, right? So this is going to be diamagnetic. All right, I. Okay, so I, just regular I, no ion involved here. So iodine, I is iodine, so we'd go down to here, okay? And it's the same idea with bromine, except now we're in, let's see, the 5s2, and then this would be 5s2, and then 5p5, but we didn't add any electrons, right? This is still, if I were to draw out the s here, and then the p shell with the 3 orbitals here, I'd get this, right? And this guy is unpaired, okay? So that's going to end up being paramagnetic. I'll just put a P. All right, zinc. Okay, so now we're getting to the transition metals. Okay, so zinc is right there. Now, if you remember, this is the 3D block. This is not the 4D block, even though we're in the 4th period. This is the 3D block. Okay, so when we filled this in, we got to 4s2, and pretending that it's not an ion right now, let's go up to zinc. That would be 3d10, right? We filled it in completely. But now we're an ion, okay, and it lost 2 electrons. Where do you think it's going to lose the electrons from, based on the rules that we've learned about the D shell before? Okay, remember a D subshell, a filled or half-filled D subshell is more stable than a filled S subshell. Okay, and so what we do is we actually get rid of the S subshell. We get rid of that 4s2, and we're left with this 3d10. Okay, and that means that they're all paired. All the electrons are paired. So that would be diamagnetic. Now, if you made the mistake of taking it out of the 3D shell and said 4s2 3d8, you would have gotten that wrong, right? You would have said, oh, here's my D subshell with 5 orbitals, okay? And you would have said, oh, here's 1, 2, 3, 4, 5, 6, 7, 8. Oh, here are 2 unpaired, and you would have been wrong, okay? So you have to understand that subshell rule with the D subshells, because it really affects how we look at the electron configurations and what kind of ions we create as well. All right, so gold plus, this is gold, okay? Let's find gold. Gold is right there. It's also transition metal. Okay, so now if I knew that this one was the 3D, this must be the 4D. So we're in the 5D subshell, which must mean this is the 6S subshell over here. So we got 6S2 and then 5D, and we went up to 9, right? Went up to 9. Now, if you remember back when we did copper, when we did this copper one right here, we actually went up to 3D10 and stole one from the 4S orbital, right? Because having a filled D shell is more stable than having electrons in the S orbital. So this is the actual electron configuration for this is X6S1 5D10. Okay. Now it's really easy to see where that plus came from, right? That just means we just got rid of the S electron in the 6S orbital. So I'm just going to be left with 5D10. 5D10 when I end up with my electron configuration for gold. And so that means if I were to draw out the 5D subshell, 1, 2, 3, 4, 5, sorry, this is going to be kind of not very good, but that means all of them are paired, right? All of them are paired. Now, if you had made the mistake of saying, 6s2 5d9 and then taken one out of either one of those, you would have been left with paramagnetic, right? But now, seeing that this rule with this D subshell, we recognize that this is now diamagnetic, okay? So I'm going to put diamagnetic D. Okay, last one, chlorine. Where's chlorine? Okay, so chlorine is going to follow about the same rule that we did for iodine, right? We're going to go up to 3s2, and then 3p, and then 1, 2, 3, 4, 5. So 3s2, 3p5, and we're not ionized. There's no extra or deficient ion or deficient electrons here. So we know that there must be one unpaired electron in that p subshell. So this is going to be paramagnetic. All right, awesome. Okay, so number 13, draw an orbital diagram showing all filled or partially filled valence subshells for each of the following atoms. Okay, so kind of like what we've been doing with the electron configurations now and drawing a little bit of these orbital diagrams, we kind of want to do that again. So with sulfur, let's look at where sulfur is. Let's go ahead and erase this chicken scratch here. Okay, sulfur is right there, right? Okay, so it was at 3s2 and then 3p, 1, 2, 3, 4. Okay, so that means I have a 3s orbital and a 3p subshell with 3 p subshells. Okay, so here's my 3p subshell. Let's say this is the 3px, 3py, and 3pz orbitals. Okay. Now, sulfur, they didn't tell us it was ionized or anything. We just have to figure out how many electrons are in here. So we knew that we filled up the 3s. Okay, we were up to 3s2. And then we got to what? 1, 2, 3, 4. Okay, so in order to fill this in correctly, you have to understand what's called Hund's rule. Hund's rule. You have to fill in each orbital one at a time. Orbital one at a time. Not one at a time, but fill in each orbital at least once before you double fill it. So I'll say orbital fill, orbital at least once with one orbital. Or with one electron. So place one electron in there. So what that means, I'll show you what that means. So when I'm putting 4 electrons into this subshell, what I have to do is go 1, 2, 3, and then go back to put 4. If you did this, you did 1, 2, 3, 4, or 4. Okay, that would be wrong. Okay, you have to put an electron at least once in each orbital before you can start to pair electrons up. Okay, because it spreads them out and it takes less energy to have them spread apart. Okay, so this is what you would write. This is the answer. Okay, this is what you would write for this problem. All right, bromine. Okay, so now bromine, we're working with which subshell? Now we're working with this 4. This is going to be the 4p subshell. So I know I went to the 4s. Okay, and we're going to skip this because it's not in the valence shell, right? We're only talking about valence subshells. So we're talking about the valence shell, which is the uppermost principal quantum number. So we got 4s2. I got 4s2 and 4p5, right? So I'm going to write a 4s, or draw a 4s2 orbital. And then I'm going to draw my 4p subshell, which is let's say 4px, 4py, and 4pz. Okay, here's my 4p subshell. Now, how many valence electrons I have? I've got 2 in here. Okay, and then I've got 5 in the p subshell. I'm going to 1, 2, 3, 4, 5. Okay, so that's what this would look like, right? Not too bad. As long as you can draw out this electron configuration and then just draw the orbital diagrams, it's really not bad at all. Okay, so silicon. Silicon is, if I draw it over here, or erase the marker over here, I got silicon right there, okay, which is in the 3p block, 3p subshell, okay? So that means I went to 3s2, and then 3p, and then how many was it in there? 1, 2. Okay, so 3p2. So I'm going to draw a 3s orbital diagram, and then put the 2 electrons in there, and then I'm going to draw the 3p subshell with the 3p orbitals. So here's my 3px, 3py, and 3pz. And I've got 2 electrons in there, right? Just like that. So this is what you would write, okay? Now, if you were not following Hund's rule, right, you would have probably put this electron in here, and you would have gotten that problem wrong. Okay, so just make sure that you follow Hund's rule, putting in one at a time. It's like the example that they give a lot is like on a bus, right? People don't usually start sitting next to each other if there are open seats, right? So electrons aren't going to sit next to each other unless there are open seats or open orbitals somewhere else. Then after it's filled, then they'll start doubling up, right? Kind of like that example. All right, so nitrogen. Nitrogen, where is nitrogen on the periodic table? It's right there in the 2p block. Okay, so I've got 2s2 and then 2p1, 2, 3. So I'm going to say 2s2, 2p3, and then draw the orbital diagrams for those. So here's my 2s, and then my 2 electrons in there, and then my 2p subshell with the 3p orbitals, 1, 2, 3, and then 2px, 2py, and 2pz. And then I've got 3 electrons in, so I'm going to put 1, 2, and 3, just like that. All right, not too bad, right? Not too bad, as long as you understand these electron configurations and then just corresponding them to orbital diagrams. All right, last one. Number 14, something is amiss with each of the following electron configurations. Assuming that the number of electrons present is correct, write down what the ground state electron configuration should be and name the element to which it corresponds, assuming they are atoms and not ions, okay? Remember that when they say ground state electron configuration, that means we have to fill in all the previous lower level energy levels first before we can start filling upper level energies. And if you skip that, then it's considered to be in an excited state. Okay, it's gonna be an excited state. So if we look at number 1, it says 1s2, 2s2, 2p2, and then 3s2. Now there's something wrong with that, right? Because when we get to 1s2, 2s2, 2p, we would have to fill in with 2p, the 2p subshell with at least 6 before we could jump to 3s2. And so this is in an excited state. So I'm going to put excited state. Not the ground, not ground. And the way that we would determine which element this is by just counting the number of electrons and then using that as kind of like our atomic number. So here we got 2, 4, 6, 8. So here I'm going to look at atomic number 8. That should have been oxygen. And let's see, they want, I don't know if they want us to write the correct, yeah, should be. Okay, so here's the correct ground configurations. 1s2, 2s2, 2p, and then we've got the two from the original 2p, and then the 2 from the 3s. So that should be 2p4, and this would be for oxygen. Oxygen. Okay. All right, so letter B, we got neon, 3s2, 3p7. So we got neon, okay, and then 3s2, 1, 2, and 3p, 7. We can only have up to 6 electrons in a p subshell, right? So what I'd have to do is actually open up a 4s1 to put that extra electron into, right? So the actual ground state for this should be neon, 3s2, 3p6, 4s1. And that would correspond to what? Here's the 4s1 right there. That's potassium. Potassium. Or just K. All right. Okay, last one. Argon, 4s2, 4d2. Okay. Let's see. It says 4s2 and then 4. Here's my 4s. But remember that this line is the 3d line. Okay, that's not the 4d. the 4D would be right below it. So here's our 4D. So in fact, all we have to change here is this principal quantum number to 3D2. So argon, 4s2, 3d2. And what would that be? That would be titanium. Titanium. All right. Awesome. Well, I hope this was helpful for problem set 8 and that you kind of got a better feel for electron configurations and magnetism and all that stuff. And we'll see you in the next problem set.